In this session, let us consider the following problem. We are given an array A of integers. We would like to compute for every index position I, the value of the next element to the right of position I, which is greater than I. If no such element exists, we let n, I, equals -1. Consider this example where A equals 6, 3, 8, 5, 9, 10, 1, 5. For every element, the next greater element is shown. The computed values are given as n equals 8, 8, 9, 9, 10, -1, 5, -1. Here is an application of the next greater element problem. Suppose we have the chronological history of the prices of a stock. For a given day, a query of interest is the first day subsequently on which the stock price was higher, and the value of that higher price. Consider a simple algorithm. For each index position I, iterate through the array incrementing I. If we come across an element greater than I, record that as the next greater element for position I. If no such greater element is found, we record a -1 as the next greater element. This algorithm takes order n time for each index position and therefore order n squared time overall. We first present the idea of an improved algorithm. This uses a stack. The idea is to stack up items whose next greater value will be determined later. This happens when we encounter a non-increasing sequence. We illustrate the idea through an example. The input array of integers is 6, 3, 8, 5, 9, 10, 1, 5. A, 0, equals 6. The stack is empty and 0 is pushed onto the stack. The top of stack entry is now 0. A, 1, equals 3. Since A1 is less than A0, the index 1 is pushed onto the stack. The top of stack entry is now 1. A2 equals 8. Since A2 is greater than A1, the index 1 is popped from the stack. The top of stack entry is now 0. N1 is set to 8. Since A2 is greater than A0, the index 0 is popped from the stack. The stack is now empty. N0 is set to 8, the value of A2. The index 2 is now pushed onto the stack. Since A2 is greater than A3, the index 3 is now pushed onto the stack. The top of stack entry is now 3. A4 equals 9. Since A4 is greater than A3, the index 3 is popped from the stack. The top of stack entry is now 2. N3 is set to 9. Since A4 is greater than A2, the index 2 is popped from the stack. The stack is now empty again. N2 is set to 9. The index 4 is now pushed onto the stack. A5 equals 10. Since A5 is greater than A4, the index 4 is popped from the stack. The stack is empty again. N4 is set to 10. A5 equals 10. Since the stack is empty, the index 5 is pushed onto the stack. A6 equals 1. Since A5 is greater than A6, the index 6 is now pushed onto the stack. The top of stack entry is now 6. A7 equals 5. Since A7 is greater than A6, the index 6 is popped from the stack. The top of stack entry is now 5. N6 is set to 5. Note that there are no candidates for the next greater elements for the index positions 5 and 7. Hence N5 and N7 are both set to -1. Here we present a Python code snippet for the improved algorithm using a stack. What is the time complexity of the algorithm? To analyze the algorithm, note that the for loop clearly makes n iterations. The while loop is nested within the for loop and makes as many iterations as the number of pop operations taking place. In the entire lifetime of the algorithm, each of n elements get pushed onto the stack at most once. It also gets popped from the stack at most once. So, summing across iterations, overall, this takes order n time. Hence the algorithm is of linear complexity. Maximal points in a set of two-dimensional points are ones which are not dominated by any other point. In the example shown, if the ordered pairs I, A, I denote two-dimensional points, what are the maximal points? The maximal points here are precisely those that correspond to n, I, equals -1. Thank you. This course is brought to you by Elahay Technologies.